I forget now whether do you have a discussant or not?
Yeah, Virginia is
Oh, Virginia's going to discuss. Okay, great. So is she here? Yeah, she's there. Hi, Jenny. Virginia, I mean. Hi. Okay, let me just get up. Have you, Josh, you haven't seen any sessions at all yet, right?
I've seen, I haven't been able to join live, but I watched video from the first 2 days.
Okay, did you watch Belkin?
I did, yeah.
Okay, great. Okay,
I
that's
was
what
even
I
going to
wanted.
refer to it briefly. Yeah.
Okay, that's what I wanted to think.
Yeah.
Um, let's see.
I'm also trying to see if there's some time. I know you said that I might be able to join. I can't join the discuss or there is no discussion today, but I'm trying to see if there's any one of the other panels that my schedule
That
would
would
join.
be great. I can add you
I'll,
to any of them.
yeah, I'll be in touch about that.
Okay. Let me just solemn duty here. Welcome everybody to the afternoon session, everybody out in the distributed land and everybody here. I'd like to introduce Josh Tenenbaum, who's professor of computational cognitive science in the Department of Brain and Cognitive Science at MIT. He's a principal investigator at the Computer Science and Artificial Intelligence Lab called CSAIL. Is that former SAIL?
No, SAIL is a Stanford's AI lab, but it's
Okay.
formerly the AI lab and the LCS, Laboratory for Computer Science,
Okay,
merged.
great.
Yeah.
And a thrust leader in the Center for Brains, Minds, and Machines, CBMM. His papers are on perception, learning, common sense reasoning in humans and machines, with the twin goals of better understanding human intelligence in computational terms and building more human-like intelligence in machines. In other words, he's cut out perfectly for this summer school. I hand it over now to Josh Tenenbaum.
Okay, great. Thank you so much, Stephen, for organizing, for inviting me. Um, you know, I got to watch much of the first 2 days, and it was really interesting to see a back and forth between people who are extremely impressed with large language models, both on their language abilities and maybe some of their general thinking abilities, and other people who are much more skeptical that they have really anything to do with intelligence, at least of the human form. The work I'm going to talk about here is an interesting, I think, mix of those two perspectives. Um, and I hope that'll be useful, stimulating, engage in some interesting discussion, both now and going forward over the next 2 weeks. Um, the heart of the talk, which will really be more like the second half, is based on this paper, which you can find on arXiv, From Word Models to World Models, Understanding Natural Language by Translating into a Probabilistic Language of Thought. But I'm going to spend the first half setting some context on just how we think about thinking, and then build on that for the relationship between language and thought. This is, I would say this is both an AI talk and a cognitive science talk, although most fundamentally to me, I'm really interested in the computational structure and origin of the human mind. So just hear it in that lens. But I think also just sort of very generally, nobody can fail to be surprised and impressed at what has happened with the most recent machine learning models. And at the same time, they're very puzzling and confounding in certain ways. So I hope to try to be able to resolve some of that, or at least point the way towards some of that. This paper, the work I'm going to talk about, is joint with a number of people. I want to single out two people, Lionel Wong and Gabe Grand, who are the joint first authors of that paper. I'm putting Lionel a little bit bigger, in part because a lot more of my slides are taken from Lionel. So I would say all of the credit for the good stuff, both on the research and in the slides, to Lionel and Gabe. And anything that doesn't quite work or make sense is probably just me garbling things. Okay. But a lot of other people contribute to the work that I'm going to talk about here. So again, we can't, who cannot be impressed with the advances of AI, whether it's in perception and robots deployed in the real world, like the self-driving car systems of Tesla and Waymo, or most recently conversational AI systems like ChatGPT. Clearly, there's something really interesting and important happening. But at the same time, something quite puzzling. Now, there's a number of puzzles that people here have talked about. Just one I'll point to is what you might call the puzzle of confabulation, which points to ways I think that the kinds of quote intelligence or unquote intelligence that we see in these systems is different in nature and origins from that in our own minds. So think about, for example, in the context of driving. This is a video from Tesla self-driving system where it's faced with something a little bit out of its training set, a horse-drawn carriage and buggy. And it interprets it as a truck, first facing one way, the other. Then it's a SUV, then it's a truck with a person behind it. Now the person's gone away. Shortly, the person will come back. They can't figure out which way the truck is facing. If a person were having this experience on the road, you would think they should stop driving and get off the road as soon as possible, right? There's something fundamentally detached about their mind from reality here. And when this happens in systems where lives are at stake, it can be deadly. So this is a serious worry technologically and societally. Now, when it comes to computer vision and Tesla self-driving, a lot of progress has been made. What I'm showing you here is from a few years ago. But you still see similar kinds of things. And also on the language side, I'm just going to show one example of analogous kinds of things that really make you scratch your head on you could find these in language models, but I'm going to talk about multimodal language and vision models because this is where, there's a lot of really interesting stuff going on where machine learning and especially like grounded language potentially might meet up with what goes on in cognition. So this is I'm just going to show you a couple of little demos from Google's large language model, multimodal language model, Gemini, both earlier versions and then the most recent version. This is the figure I'm showing here, which I'm giving to Gemini. And I should say you can see similar things with ChatGPT, but it's a little bit funnier with the Google one. So I'm going to focus on that. This is an image from my colleague Vikash Mansinga, whose work will also figure in the talk. Vikash is one of the world's experts in probabilistic programming. He and I are very interested in how our minds and our machines could model uncertainty. So here's an image that I think all of us, when we look at this, it's pretty clear that, though it's a little hard to read, kind of messy, it's really clear that there's a word here and that the word is uncertainty. But what does an LLM, a multimodal LLM, see from this? Well, it might see this. The image you sent me shows a black and white image of a text box. The text box has a dark gray border, rounded corners, good. Inside is the word dream, written in a bold sans serif font. Is there anything else I can help you with? I ask, how many letters are shown in the text box? There are 5 letters shown in the text box. The letters are D, R, E, A, and M. What is going on with this? Now we could say, all right, well, at least it's pretty good. I mean, at least it's recognizing that there's text and it's, it could be worse, but it seems to be strangely confident about an incorrect answer. But you could say at least it's not like seeing a person or person walking down the street. But consider this small change to the input image. Now our LLM says, this shows a black and white pixelated image of a person. The person is facing forward and appears to be standing still. Here are some details about the person. They have short hair, they're wearing a shirt with a collar, their legs are slightly wider than their torso. Since the image is pixelated, it's difficult to discern other details, such as facial features or specific articles of clothing. Now, again, the thing that I think should make us puzzle here is not just that the system gets this wrong, but that it seems to confidently assert things that are so detached from our sense of the reality of what we're seeing, and where just a small change can make such a huge difference. Just to update things, this was from the first version of Google's Gemini. The most recent version of Gemini 1.5 Pro has gotten better in some sense. Now, given uncertainty, it doesn't say dream, it says optical illusion. But it's still wrong, and it's still overconfident. It rates itself as fairly confident that it says optical illusion. It's interesting. It makes you think, is there some semantic association between dreams, optical illusions, and this particular way of presenting the notion of uncertainty? I don't know. The very most recent thing, this was, well, it's not that recent, but the last time I gave this talk, I tried this on the newest updated version of Gemini 1.5 Pro, just to see if perhaps it had been improved. And now it gave a very different answer. it didn't read it as optical illusion. It gave this extended digit number 61298153242, and I asked it to judge its confidence, and it said, well, 70 to 80%. Again, what? What happened? Just to check, again, consistency and coherence of this weird interpretation, I asked it just 10 seconds later, just out of context again, just gave it the same thing. And the next 10 seconds later, it said geocache. Again, now 75% confident. And then one more time, a distorted text appears to read northeast blackout. However, it's difficult to be certain, but it's moderately confident that the text reads northeast blackout because the first and last words are relatively clear, while the middle word is slightly less discernible, but still suggestive of blackout. Okay, so what's going on here? That's one of the mysteries. Now, I'm going to gesture at what I think some of the mysteries or some of the answers might be, but mostly to point the way towards the difference with human intelligence and what we're trying to understand in our work. Okay. I think fundamentally what's going on is whether you're building a computer vision system or an LLM or a multimodal language text system, you're building a system that takes the inputs and outputs that our brains do, perception of the external world, sense data of some form, and it produces actions or something like actions that can be grounded back in the external world. But the inside of the system doesn't have any notion of a world. It's a function approximator. It's learning to approximate the input-output functions that our minds produce. And it's learning to do that from various data sources, including objective data sources, as well as human reinforcement. Now, why does this possibly work? Well, again, there may be some laws of physics, things that are like physics, like, for example, the famous scaling laws of neural language models, where you can show in some form, especially when you're trying to predict, like, and this is very much following some of the information theoretic ideas that Richard has been talking about and others in the group here. If I'm just trying to predict the next token from the previous ones, there are certain fundamental power laws of language and distributions in language that these systems seem to incorporate and build on, such that if you increase by an order of magnitude the amount of compute, you can, in a predictable way, lower the test loss in predicting the next token. That's on the left. In GPT-4's technical report, they suggested that you could see similar kinds of scaling laws for problem solving, not just text prediction, although it's a lot iffier there. And I think fundamentally the problem is the power laws are beautiful laws and they're predictable in a certain sense. The thing about a power law is while it approaches asymptote, or rather it approaches zero error in its asymptote, it, in some important sense, never gets there. Compared to like an exponential decay, where there's a predictable timescale in which it will get to zero, a power law keeps slowing down. And if you have any uncertainty in the power law's coefficient, or in its applicability to not just to predicting the data stream, but actually solving a problem, then it's basically impossible to know how much data and compute you're going to need to actually get to the asymptote, which we want to call, full adult human intelligence. In contrast, humans don't seem to be built this way. Our minds seem to be built as world modelers from the start. And I'll say more about this, but from the very beginning, we have our minds and our brains, and this is something that shared with other animals and inherits from our evolutionary legacy, seem to be built to model the world and to deal with all kinds of incompleteness and uncertainty. And that means both in the structure of the world, and our uncertainty over what's out there, the current state, as well as the fundamental deeper laws, the causal laws of physics, or how agents plan and so on. But we're built to engage these kinds of mental representations. As I'll show in a little bit, the way in our group we've modeled this for a long time is what we call the game engine in the head, by analogy to, say, video game engines. Our brains and minds seem to be built with these kinds of resources for world modeling. You can see that these notion of world models that are used even not just in human adults, but in young children to coherently understand the world and deal with situations that are importantly out of distribution, right? And that's really key. The ways in which we perceive and learn about the world are not nearly as tied to the distributions of our experience as a machine learning or function approximation approach. So here's some examples of different kind of self-driving system. These are 4-year-olds for the most part, 3, 4, 5-year-olds, in a genre of YouTube videos. You can see one of them, actually, the video on the left. It's sort of the video genre on YouTube is like, my 4-year-old driving for the first time. And parents have put their kids behind the wheels of golf carts or tractors or cars or trucks, and just go at it. And they video from the side or from next to them. And you could question the rationality of the adults who are putting their kids in the situation and then putting the videos online. But there's a certain basic rationality that the 4-year-old has. Even though they haven't been in the situation before, the systems that their mind has built through evolution and the last couple of years, the first few years of their experience, allow them to handle this totally new kind of perceptual information. The world's going by them at a high speed, and they're in control in some way. But they can generalize from their experience because the nature of their generalization is their mind's models of the world, and those transfer to these new situations. Of course, there are new things they have to learn about exactly how the steering wheel works, but they can learn those very quickly too, because the learning is grounded in their world model. So fundamentally, I think what we have is a contrast between the scaling thesis of deep learning and today's AI and what you could call the original scaling route that human intelligence follows, what we might call growing up as opposed to scaling up. And I want to contrast 3 points, which I think are really important for understanding, in general, our intelligence and the contrast between AI and machine learning, and especially the role that language and language models play in this. So 3 points that are fundamental to the way today's AI is working based on deep learning. One, that intelligence is seen as the end result of learning, where learning starts with some simple, very general, and in some ways dumb mechanisms, associative learning, prediction, in some way. But the idea is if you scale that up enough, you have this surprising emergent phenomenon that now we start to call intelligence. The problem is, though, I mean, either you could call it a problem or you could call it just the way things work, but there's some remarkable kind of generalization, but it still is going to depend on similarity to training data. And its ability to go beyond the training distribution is weak and unpredictable compared to when you're in distribution. This is true whether you're talking about perception or other forms of higher level cognition, but especially thinking, things that we recognize as forms of reasoning, planning, problem solving, and so on. The sort of thing that we've never seen in any computer vision system, but we're starting to see some interesting kind of approximation to in language models. Crucially, that in machine learning, thinking derives from language because it's only the data of language, not the data of pixels, that conveys information really about human thoughts, which makes sense. Again, humans have always used language as our main medium to express our thoughts to others, just like what we're doing right now in giving talks like this, right? But crucially, thinking requires language data and even carefully cleaned and curated language data. Our colleagues who are at the big AI companies can tell us a lot more about this, or rather, maybe they can't tell us about this, but they can tell us that they can't tell us about, and those of us who've worked with this know the importance of having the right kinds of language data as well as the right reinforcement data. Okay, so contrast this with human minds and especially human children. For our intelligence, it's not just the thing that is at the end result of all of our learning. Although we do, babies are not in some important way, not as intelligent as human adults, we would like to say. But human intelligence is built in some form from the start. It's the foundation of learning. It's not just the end state. It's what's there and the learning mechanisms that let you learn so much from so little. Okay. And we saw some of that in Virginia's talk. And, I think that the field of human cognitive development is a testament to this, or what I was just showing from the 4-year-olds is another example. But in other work that I'm not going to talk about here, we've done a lot of work trying to model the core knowledge of even, 12-month-old or 10-month-old babies. And there's important ways in which they have a common sense understanding of the world that is in significant ways, it's not all built in, but in significant ways, it seems to be present even in 2- and 3-month-olds. Okay. As a result of our built-in capacity for modeling the world, our generalization is based on the fit of our mental models. It's not about the training data. Okay. Data is important. We improve our models, we grow models, we can make new models from data. But what accounts for generalization and what drives generalization is not similarity to the data, but the fit of our world models and their ability to be flexible and themselves to be generalized. Okay. And crucially, thinking isn't the thing that comes at the end state as an emergent property of modeling language, but rather thinking is there from the start, and it's the basis for language. It's the basis for why human children construct language so robustly and resiliently. And again, there I'm referring to by using that word resilience to some of the ideas that Virginia talked about in her talk and Susan Golden Meadow has talked about. I urge everyone to watch her Rumelhart Prize talk where she talks about this as well. This idea that, as we saw in Susan's work and Annie Sengus's work with Nicaraguan Sign Language, that children who grow up without any language input, it's not just about the poverty of the stimulus in the traditional linguistic sense, but you grow up with deaf without sign language input, and you create in some form your own personal proto-language, or at least a way of communicating that has hierarchical symbolic structure. And then you bring a few such children together, and within the span of a couple of generations, they've created a whole new language from scratch. Okay, so it's very clear from data like that humans are built to think, and we're built with a desire to understand and to be understood, to express our thoughts in some form and share them with others as our social partners. And that's, there's nothing I think more fundamental to understand if we want to understand where our intelligence comes from. So what we've been trying to do in our work is to try to capture the human growing up scaling route in computational terms. And it starts with this idea of probabilistic inference and expected value decision making on top of world models. Informally, I would say, and like many others, that thinking, not just in human brains, but in brains in many other animals, is about making good guesses and bets, not about the next data thing you're going to see, not about the next token or the next pixel or set of pixel values, but about the world, what's going to happen in the world and how it might depend on your actions or the actions of others, or how you might be able to change the world to change those dependencies, causal and counterfactual reasoning. And then having some sense of what you'd like to see happen, and what you'd not like to see happen, or what could really cost you your life or be hugely valuable, and making good bets about how to act and what to think about next. Fundamentally, it's this classic idea of effectively rationality that you could say our minds and brains are the original sources of this idea through evolution being constructed to do this kind of computation. In our work, and this is the stuff we've been doing with language models builds on this, we've been using the idea of probabilistic programs, which is a family of mathematical languages and actual programming languages and platforms to embody this idea, basically take this conceptual idea of rational world modeling, inference, and decision, and turn it into practical engineering terms that can be models of human minds as well as more human-like AI. And I don't have time to give a whole introduction to probabilistic programs, but you can think of it as a kind of catch-all phrase or a complicated suitcase phrase, just like neural network packages a number of different things together. But probabilistic programs are formalisms for combining what I think are several of the best ideas about intelligence that have come up through a number of decades in the field. That includes neural networks, modern probabilistic programming languages like Gen from Vikash Mansinga's group, who I mentioned before at MIT, or Pyro, that was developed by originally a group at Uber AI that Noah Goodman, another collaborator of ours, helped to start, along with a number of others. In many ways, build on languages like PyTorch or TensorFlow, the languages that support modern deep learning and that allow you to construct really complex but end-to-end differentiable functions for approximation or other purposes. But that's not the most important part. The most important part are building on the idea of symbolic languages for expressing abstract knowledge, for modeling the world. That is, across many areas of science and engineering, consistently the strongest, most powerful toolkit we've had for building coherent models to understand the world are various forms of symbols. And then the third idea is the probabilistic one, using those symbolic languages to express probabilistic models where you can be uncertain about everything. And in a Turing computational sense, you can be uncertain about the state of the world right now, or more abstractly, how the world works, how the different kinds of data that you're getting, perceptual or others, are connected to the underlying state of the world. And then to be able to do joint inference about all those different sources of uncertainty as the basis for perception, reasoning, planning, learning, and so on. And probabilistic programs bring those things together. I'll say a little bit about how that toolkit works, as well as then how, once you learn language, the ability to externalize and internalize thoughts that are produced by these kinds of probabilistic programs, basically, that transforms things in fundamental ways. And here, lest people think that I'm just a deep learning or a LLM skeptic or something, Again, I find neural language models and the long tradition of distributional statistical learning in language that they build on to be really important. And in the work that we've been doing, we've been using large language models, or in many, by today's standards, I might even say small language models, to capture this, actually. So I think this is a place where I would not say that if you want to think about human minds, it's LLMs or transformers all the way down, nothing like that. But the kinds of things that are going on in distributional sequence learning could be a way to capture some aspects of how language grounds in these tools for mental modeling and also enriches and extends it. So, I mean, just very briefly for people who aren't familiar with this idea, for a couple of decades now, I and many colleagues, students, former students, a number of others who are very interested in what you could call the Bayesian approach to cognition, have been using this general toolkit of probabilistic inference over structured symbolic models to capture many aspects of mental models. And this is a plug for a book that's forthcoming, edited by Tom Griffiths, Nick Chater, and myself, and with many, many other contributors. And it'll be coming later this year from MIT Press. But it's part textbook, part research monograph, and just showing how this toolkit can be used to capture, to both explain in a principled and actually understandable way, but also to quantitatively predict and model behavioral data across so many different ways in which our minds model the world. Just to illustrate one, which I'll come back to in the context of language in a minute, an area that we've done a lot of work on is intuitive physics, as a kind of probabilistic inference. And the particular kinds of intuitive physics we're thinking about are in these complex scene understanding cases, which, again, not coincidentally, I think are also really interesting and classic settings for studying grounded language. So, for example, if I show you a scene of a bunch of blocks, think like Jenga blocks stacked up in various ways, some of these images might look very stable, others might look unstable, and I can ask you a question. How likely do you think this stack of blocks is to fall under gravity? And we can model that by having a structured world model, which consists of basically 3D object models, and then causal models of how those underlying 3D scenes give rise to images. That's like a graphics program, basically. The computer graphics is a way of writing programs that generate images from those underlying 3D world models. But then there's also these physics programs. And again, here I mentioned game engines. So game engine style physics simulators capture a lot of aspects of effectively real world but common sense physics in ways that hack Newtonian or actual untrue scientific physics in all sorts of ways to be efficient, but do a pretty good job of capturing what we expect to happen in the world, which makes sense because we're the ones playing the video games and they're designed for us. So by doing probabilistic inference to infer the input to a graphics program, given the output, which is the image, you can do a lot of 3D perception. And then by doing probabilistic forward simulation, you can imagine what might happen next. It could also be conditional on your action. So the same toolkit could be applied to a much less familiar sort of judgment. Like, imagine I have these scenes of red and yellow blocks on a table, and what if I bump the table hard enough to knock some of the blocks onto the floor? Will you knock off more red blocks or yellow blocks? So the first judgment, the one about how likely is a stack of blocks to fall, I mean, anyone who's played Jenga or anybody who's ever been a kid probably has built things. If you're a professional builder, you have a lot of other intuitions. But, that's very familiar. The question on the right is one that, unless you've seen me talk about this, you probably never thought about. It's not something you have direct experience about. You can't learn it from feedback, how to answer that question. But I can use my language to give you that question as well as the other relevant world knowledge, and then you can reason about it. And the models that we build can capture both the familiar judgments of like how likely the stack is to fall, as well as these novel judgments relatively equally well. So these scatter plots are examples of the kind of data and modeling that we've done in our lab for a long time. On the y-axis, we're plotting the average human judgments of, let's say, on 1 to 7 scale, how stable or unstable the blocks are. And on the x-axis, the average result of doing a small number of probabilistic simulations where we imagine running forward game-style physics a few time steps with uncertainty about exactly where the blocks might be and how the physics works, because these are all things that our minds don't fully know. The same kind of model can be used to answer these red and yellow questions. So just to illustrate this, if we take one of these scenes and we reconstruct it in a game-style physics engine and we simulate a bump of the table. So there's one simulation. On the right, I'll show you another simulation with a harder bump, okay? And you can see, watch it again, that different things happen in these two simulations. But it doesn't really matter which one of those you ran to answer the question, right? I mean, you look at the scene also, and it's very clear from the beginning that if I bump the table relatively hard, it's going to probably be mostly yellow blocks on the floor. How do you do that? Well, in our model, you only need to run one or a small number of these simulations to answer the question at the grain of intuitive physics. And you don't need to run it very long. You could stop it now and you already know the answer. Okay, so a small number of short, incomplete simulations is the basis for these pretty quantitative models, and they've also been used in robotics to actually predict and be able to get, for example, a robot to learn to play the game Jenga, but learn from a very small amount of realistic human experience. The same kind of idea has been very impactful, I think even more impactful in intuitive psychology, where we and many others, there's work that I've done with a number of students and my colleague at MIT, Rebecca Sachs, but especially I would highlight work from Chris Baker and Julia Har-Ettinger, who did quantitative modeling here going back years with us. Julian continued, Chris is now working on self-driving cars in industry. Julian is now working on is now a professor at Yale, where he's extended on this kind of approach in many areas of social cognition and communication in really interesting ways, and many other colleagues here. So I should mention also, though I forgot to mention this before, the intuitive physics work started in our group more than 10 years ago with Pete Battaglia and Jess Hamrick and others. And they are now actually both working at DeepMind, Google DeepMind, working on various interesting kinds of deep learning approaches for both intuitive physics and all sorts of real world physics that matter, like climate modeling. That's where Pete's current focus is. I won't go into the details on the Bayesian theory of mind, but the basic idea is, again, there's a program that now describes not necessarily how actual minds and brains works, but our mental models of other minds, how the actions we see agents take, we interpret them as the effect of planning programs that take as input our mind's representations of their beliefs and desires. And by seeing how agents act and change the state of the world and modeling also their perception process, which leads to belief formation and updating, we can model many aspects of how people understand other minds, especially in what you might call these sort of physically grounded and perceptual scenarios, the kinds that you can also study in young babies, like in the experiments I'm showing here from Gergely Chibra, Kylie Hamlin, Paul Bloom, and others. The intuitive psychology case is especially interesting because in work that we've done, like in this paper with Brendan Lake, Tomer Ullman, Sam Gershman, that helped to set some of the current stage of debates between deep learning and more cognitive approaches to AI, where we put out a challenge back in 2016 and 2017 for the deep learning AI world about how to think about the kinds of inductive biases, mental model materials that seem to be built into human minds and the learning mechanisms that build on those. We highlighted both intuitive physics and intuitive psychology. In the famous Sparks of AGI paper, showing again some of the most earliest glimpse into some of the surprising things that GPT-4 seemed to be able to do, Bubeka and colleagues also highlighted intuitive physics and intuitive psychology. And then in a recent paper from Eric Schultz's group, which is kind of forms a three-part story here, and it continues as I know Bushoff and Schultz and colleagues continue to work on this area, and we also do, is to now in the era of these multimodal language and vision models, like I showed you at the beginning, we can go and take on all these tasks, like whether it's block tower intuitive physics things or agents moving around in the world and interpreting, as Julia Har-Ettinger called it, the naive utility calculus of their rewards and costs, and give language models or multimodal models the same kinds of stimuli and questions that we give people. And as Schultz and colleagues showed, in some of the intuitive physics settings, they're kind of okay. They're not great. In the intuitive theory of mind ones, they fail altogether. That's a quote from their paper. So as an example, this is work that Julia Har-Ettinger did as part of his PhD thesis with myself and Laura Schultz, where we call these the astronaut studies, where people would see an agent, an astronaut on some planet, who would start at a certain point and have a home base that they had to get to. And they would follow some path along the surface of the planet. They could just go straight to their home base, or they could take a not straight path. Crucially, there were various objects that they could pick up that could either be positively valuable or aversive to them. And we asked people based on the path, how likely do you think that the agent likes or doesn't like one of these objects? And also, there are different terrains, and the terrains could be more or less costly. And by showing people different maps, different configurations of object space, terrain, and different paths, you could get very interesting, rich inferences about what the agent both wants and what the rewards assigned to the different objects are, as well as the costs for moving around on the terrain. So here's an example of some of the stimuli from one experiment, just to show you the kind of variation. And then in each of these cases, we can ask people to make 4 judgments, or 3 or 4, depending on how many kinds of terrain. And that's what's shown here. These are actually the predictions of the model, z-scored, for the relative cost for the different kinds of terrain and the relative value for the different kinds of objects. And we're assuming that the agent basically takes a rational, efficient plan, trying to maximize reward minus cost, where there's a small cost for each step, but especially costly when you travel over certain kinds of terrain. So seeing the path, you can make inferences about how the agent has rewards and costs. And then when you ask people to make the same judgments, they line up almost perfectly. This is just one of many experiments that Julian did, showing what is really a remarkable quantitative match. But by a model that isn't just fit to data, there's a little bit of fitting, but it's mostly based on thinking about what are the core concepts of theory of mind that people like I mentioned before, like Garrigues and Chibra, have studied even in very young infants, pre-verbal infants, infants who can't even walk, and barely have just able to reach for things themselves, yet they still have these ideas, these intuitions about efficient inference and use those. It seems, I should mention Sherry Liu's work, who was a PhD student at Harvard a few years ago with Liz Spelke, who worked with Tomer Ullman also and me to show those same kinds of things work in babies. Sherry's now doing amazing stuff, extending that in a new lab at Johns Hopkins. So these are cases where this kind of probabilistic program model works really well, but just a pure language model is basically at chance, zero correlation with human judgments, although quite good at telling you things like the background color of the scene. Okay, so in the last part of the talk, having sort of set the stage for how our human thinking seems to work and how we can model this in ways that are explanatory, understandable, and quite quantitatively predictive using these probabilistic programs, let's understand where language comes into the picture. I don't think that a pure machine learning transformer approach like the ones we've been talking about are on track to give a human level or certainly a human-like account of how it works. But I do think the ideas of sequence modeling, statistical distributional learning that you see having such great success in LLMs, even perhaps on a smaller scale, could say something important about how language comes into the picture. So this here is, at the beginning, I talked about this archive paper, the Word Models to World Models paper from Lionel Wong, Gabe Grand, and colleagues. And that's what I'm going to be talking about here, is how we've been bringing these tools together. But a key ingredient is this, I would say, the modern return of the language of thought hypothesis, made famous by Jerry Fodor, but obviously with a history that goes back hundreds, if not thousands of years. But in a number of recent papers and proposals from various groups, the idea that, again, that there's some kind of not necessarily single language, but abstract symbolic languages, which could be general or also created and constructed domain-specific languages. Some kind of abstract symbolic language seems to be a powerful way to think about human thinking, abstraction, concept learning, and so on. And the particular kind of languages of thought that we've been thinking about are what Noah Goodman and Toby Gerstenberg and I called the probabilistic language of thought. So this is the idea of using probabilistic programming languages, the technical tool I talked about before, to formalize in a cognitive setting a certain kind of hypothesis of a language of thought, but one that is focused on modeling the world, not just possible worlds, but probable worlds, and where the symbolic language can also express ways of conditioning and querying so that we can ask and answer the kinds of questions that our minds do and that we might want, for example, any kind of general AI system to do. So if you want to learn more about the probabilistic language of thought, check out our chapter in The Conceptual Mind. This is one of the Margulies and Lawrence readers, or the web book Probabilistic Models of Cognition, which has examples of the kinds of models I'm going to be talking about. Not with language models, though. The new thing is to take advantage of LLMs, and specifically the fact that most LLMs these days are trained not only on natural language, but on programming languages and source code, namely programming languages like all the ones we're probably familiar with that are designed to be read and written by humans and not just machines. And so they're written in a very English-like way or natural language-like way. Linguists have long pointed out sometimes the differences between natural languages and programming languages. But from a certain perspective, they're a lot more similar than they are different. A hierarchical structure, syntax, and even just much of the lexicon. Natural languages, they're not just commented, or programming languages are not just commented in natural language, but functions, variables, data structures are named using English for the most part. Okay. So that's a very powerful data source that allows some kind of statistical sequence-to-sequence model for predicting and translating between streams, sequential streams, to effectively learn to translate from English or any other natural language into programming languages of thought, and that includes probabilistic programming. So the idea of this paper, what we call rational meaning construction, that's the name of this, is a particular thesis on how language is understood, and perhaps also how it might be produced and learned, although our focus here is on language understanding, and thinking about the relation between language and thought in that context. By thinking, what we think of as the core original notion of thinking is what I've been talking about for the first part of the talk, which is the idea of having a structured probabilistic model of the world, conditioning it on observations, and then drawing samples of underlying latent states and future states. Okay, that's thinking from this standpoint. And then understanding language is effectively translating from natural language into a probabilistic language of thought that's used to define and condition and query the probabilistic world model. So we're going to exploit the property of these LLMs to translate from natural language to code in a way that might be familiar if you've tried using them to code, but it's different in some key ways. In particular, we're not going to be just asking our LLM to write a whole bunch of code, at least not to start, but we're going to be focusing on the sentence level and what is meaning at the sentence level. It's something like trying to infer a line of code in a mental programming language that is your best understanding of the meaning, by which we just mean the thought that the person who's uttering that sentence is trying to convey. Okay. And the LLMs in this case can represent that meaning construction function, okay, in ways that have some very interesting properties. So I'll just illustrate this with a classic example from the probabilistic language of thought literature, the so-called Bayesian tug of war. So just to ground this, imagine that you're reasoning about a situation like, for example, various games of tug of war, various people symbolized by colored shirts here are facing off against each other. And let's just take one person. Let's just say this is a guy named Jack. And you might say, well, how strong do you think Jack is? I haven't shown you any information, so your best guess might be just average, okay? Now, suppose I give you some other information, like, or I should say, here are a few samples. I might say average, maybe he's a little less than average. If we're talking about MIT students, we might just pick the MIT average. But now I could give more information, like suppose you know that Jack beat Leo in a game of tug of war. So that might move your arrow up from the MIT average, because, well, people who are stronger might be more likely to win than people who are weaker somehow. Okay. I could give you some more information, like Leo had just won 10 previous matches. Well, so that means you might think Leo's pretty strong and Jack must be even stronger. So your arrow goes way up. But suppose I told you, well, Leo sometimes just doesn't pull as hard as they really could. So maybe Leo was just getting a little lazy when Leo faced Jack. So it might go down a little bit. But then Leo single-handedly beat a team with Jack and Tom on it. Okay, so now you think, okay, well, Leo was probably lazy before. Jack maybe isn't that strong, since Leo, when they wanted to, could beat both Jack and Tom. Okay, so the point is, in a classic example of non-monotonic reasoning, your inference about this one aspect of the world, Jack's strength, is going up and down as you get various information. So we'd like to understand how that thinking process works, how updating your beliefs based on linguistic evidence, linguistically expressed evidence, works. Okay, that's the starting point of this paper. And the idea is to use, in this case, we're using the probabilistic programming language Church, which is based on a dialect of Lisp or scheme. So there's a lot of parentheses, and I'm not going to be able to unpack all the language, but hopefully you can get the basic idea that we define functions that describe probabilistic distributions on strength, laziness, and so on. I'll work through this. And that's well attested work that's been very good. It's basically the general toolkit for doing the kind of probabilistic intuitive mental modeling that I showed you with intuitive physics and intuitive psychology. But here we're doing it for this kind of novel domain. There's no core domain that infants are born with for tug of war, but we can write a model like this to capture what adults in our culture at least might think. And then the key new thing here is to understand how to ground language in these mental models. So this is where we're going to model the translation of a statement in English like Jack won against Leo, or a question like how strong is Jack, into lines of code that support probabilistic updating and querying in this language. Okay? And the meaning functions, which will be implemented by the neural network here, or the large or even small language model, capture various interesting ideas that have been proposed. I don't have time to review this history, but proposed in different eras of linguistics and thinking about how to think about meaning, how to think about concepts, and it's a very rich literature that I'd be happy to try to discuss if we have time during the question period. Okay. But the hypothesis here is that maybe these distributional language code models can implement some human-like, perhaps, approximation to this meaning function. And again, crucially, we're not trying to now capture to learn patterns in data in the world. We're trying to learn patterns in our thinking and how thought is expressed in language. So it's a more modular problem, which I think is better suited to the way language actually works in the human brain, right? There's a delimited part of our brain that is a language processing network. Strokes or other lesions there can really impact your language ability without impacting your general thinking ability. And it's a relatively late evolutionary addition to a brain structure which shares a lot with other non-human primates, for example. And so it's that modularity, I think, is also really important here. So again, just to unpack how this works, you have a probabilistic program that describes these concepts that I can describe to you in language in this way, but to the model right now, they're just given in code, and they just describe, for example, that player's strength is drawn from a Gaussian distribution. Players can occasionally be lazy. When you're lazy, it cuts your effective strength in half, and the strength of the team is the sum of the total strength that the members pull with at any one time, and the stronger pulling team wins. That's basically what this says. Now, for now, we'll just assume that you have that kind of mental model of a tug of war game, and we'll just talk, how do you update your released language? And the basic way of doing it is that we're using what I would call now a medium language model. We used OpenAI's Codex, which was the first widely used code LLM, pretty small by today's standards, much smaller than GPT-4, kind of like an early version of GPT 3.5, to translate from a sentence in English like this into what in Church, the probabilistic programming language, is called a condition statement. It just expresses the constraint on possible worlds that while the underlying define statements define stochastic or probabilistic functions, which give you probability distributions on possible worlds, this says we're going to restrict our probability distribution, which is like our prior, to a posterior, just those worlds that are consistent with Jack beating in one match Leo. Okay. And then similarly, a question to a query statement, like how strong is Jack, turns into this query, which the probabilistic programming language then basically evaluates. It draws samples from possible worlds consistent with the condition and generated from that prior on the left, and checks what the strength is, and then just kind of counts up those distributions. So it's a kind of probabilistic mental simulation, effectively the same, or a generalization of what we were doing in like those intuitive physics examples. And from this one piece of data, Jack beating Leo, you can see the posterior updates from the prior. So Jack is stronger than average. If I say, oh, Jack also beat Alex, or proceeded to claim victory from Alex, that turns into another condition, and that updates the posterior even more. So now, well, Jack's a lot stronger than average. Even working as a team, Leo and Alex still could not beat Jack. Wow, now Jack's even stronger when you add in that conditioning statement. So again, where the LLM is coming in here is it's just adding in the statements into the language of thought, and then we're running inference in our probabilistic programming language to give these answers. It's worth, and this is, again, especially if we want to understand what I think is the way forward to thinking about how meaning in language works in humans and where LLMs can come into the mix. What's really powerful about neural language models here as ways to parameterize a meaning function is the ways that they can pick up on statistics, context, pragmatics, metaphor, semantic associations, all the things that in many ways were most appealing in connectionism, like distributed content addressable associative memory and distributed representations of graded semantic associations. So for example, the LLM will translate Jack won against Leo, which into this statement, which looks like a fairly transparent semantic parse of that natural language. But it'll make basically the same semantic parse of a sentence which on its surface, and in traditional language structure analyses looks rather different, right? The syntax here is more complicated. I'm not actually using the word win, but in the context, the relevant aspect of meaning for thought here is the same. Namely, this is just another way, maybe a more poetic way, or dramatic way to say that Jack won against Alex. And the model knows that automatically. It doesn't have to be specially prompted or trained for that. It's using its associative memory properties. It's also distributional. These are probabilistic models, not on worlds, but on strings. And in this case, they're probabilistic models on strings in our mental programming language. So they can bring in classic notions of vagueness. If I say Jack is strong or very strong, I'm not telling you exactly how strong Jack is, but you might interpret that as a distribution on different condition statements saying, well, Jack's strength is greater than some threshold, but I don't know what that threshold is, but it's probably pretty big. Remember, in this case, the mean is 50 and the standard deviation 20. So 80 is, 1.5 standard deviations above the mean. And the idea is this is, again, like in scalar adjectives, it's basically saying I'm conditioning on the idea that Jack is greater than some threshold, but I could be uncertain about what that threshold is. And even metaphorical things, like if I say Jack is pretty strong and Ben is a beast, right? In this context, it's reasonable to interpret Ben is a beast as saying Ben is really, really strong, 80, where Jack was maybe 60 or greater. In a different context, if I'm talking about, whether you should date someone and I say Ben is a beast, then I'm probably saying, stay away, right? So that both metaphor, sort of context sensitive metaphorical interpretation is the kind of thing that this meaning function is very good at. I'll mostly just skip over this, but in work with Ben Litkin and Leo and Gabe and others, we've done, and this is really all Ben's work, some very nice quantitative studies of showing that these contextual aspects of understanding of strength in the kind of tug of war context can match very nicely, not always, but in a lot of cases very nicely with human judgment. So it's suggesting that the distributional aspects of meaning that we're capturing here are at least somewhat, if not psychologically real, at least consistent with the judgments that people make. Okay. But mostly what I've done with this example is just to try to show you how this kind of framework can work to be a way of implementing what is in some sense a classical idea, that language isn't directly the medium of thought, at least the only one, but it's a way of expressing and communicating thoughts, internalizing and externalizing them. Okay, and that statistical distributional mechanisms can be a powerful way of learning that the mappings from the signs and symbols that we externalize to an internal compositional structured language of our thought. Now, a lot of what goes on in this paper, and I'll just show you one or two examples, such as work with Zed Zhang in an intuitive physics domain, or some intuitive psychology work with Lansing and Shen, or Tanshi Shen, is showing how we can take the same kinds of things that I showed you in the first part of the talk and effectively reconstruct them, but now in worlds that are just described by language. So imagine, take that task of the red and yellow thing, where before I was showing you the image of a scene, and then I was using language to describe a question. But what if I just use language to describe the whole world, right? So I didn't show you an image, I just described what's there. In many ways, but we're still going to do a mental simulation, a probabilistic mental simulation in a physics engine. There's many cases, in our daily life where we use language to describe the physical world as we experience it. It can be extremely expressive, very complementary often to, images or photos. It has vagueness and uncertainty, and that's interesting. So we might describe a scene now, like imagine a table and there's some blocks on it. There's some red blocks in the center. There are many tall stacks of yellow blocks on the side of the table, if the table is bumped hard enough and so on. So we ask the same question, but for scenes that are described in language, and then people make a graded judgment, the same 1 to 7 graded judgment of is it more likely to be red or yellow blocks. And so when we can test this again, the same kind of quantitative study with large number of participants, all online, all just reading stuff, with different kinds of language expressing exact as well as approximate number, approximate quantifiers, logical quantifiers, vagueness like the stacks could be tall or very tall, and different kinds of spatial relations, and across many different stimuli, we mix up more or less complex sentences using these different kinds of language. And in each case, we're using, again, a relatively small LLM to translate sentence by sentence into statements for conditioning and querying in our probabilistic language of thought. Then we run a small number of mental simulations, in this case in a 2D physics engine, compute the outputs and compare those with people. And what I'm showing you here is, again, the same kind of scatter plot I showed before, but on the vertical axis are again, our human judgments. And on the x-axis now are the model or the predictions of this language-informed thinking model. So it looks a lot like what I showed you before. These are the judgments from the Battaglia et al. Work on the red and yellow task. Where here the model was given a visual scene, people were given visual scenes, and the model did that same kind of probabilistic mental simulation in the physics engine. But in the current work on the left, again, the scene description is constructed from language using the tools that I've shown you by conditioning a prior on scenes. Okay? And the main point is just that the models fit human judgments pretty well in both cases and about equally well, all right, which is interesting. We can also compare with just a sort of zero shot or a few shot baseline LLM. So these are language models which don't have an explicit mental model of physics or any doing explicit simulation, and they are much worse fits to people. Okay, this on the high up here on the y-axis is distance and distribution from human distribution of responses to the various models. The blue one is the rational meaning construction model. And you can do a similar thing in the intuitive psychology domain, like, for example, in the settings that I showed you with Julian Haar-Edinger's work. This is work that Lance Ying and Shen did. I won't go into the details, but again, we can describe worlds with various goal objects that an agent might have and constraints, like you have to go through doors. The doors could be locked. You have to use keys. There could be a red key that could unlock the red door, and so on. People could be told either that, you need a key of the right color to open each door of the same color, or you could be told weird things like keys only unlock doors of other colors. Okay? In these kinds of worlds, again, the rational meaning construction model does a very good job of capturing people's judgments. For some kinds of judgments, easy cases, even GPT 3.5 does reasonably well. GPT-4 does better. But as the situation gets more complex or unusual, things change and break down. Like especially if we say, well, in this world, keys only unlock doors of different colors. That's an easy thing to say to somebody, and you have to change your mental model. But when you do something like that, GPT 3.5 becomes anti-correlated with people, and GPT-4 just drops from being highly correlated to just being a chance. So these are examples of the ways in which, going out of distribution from our training experience, if we're just using a machine learning function approximation approach, which is remarkable as those systems like GPT-4 are, that's what they're doing. But ways in which, if the function approximation is just approximating a much more modular translation function and building on our mental model tools, we can just do much better. Okay. The last thing I'll just talk about very briefly is, what is any work like this has to raise more interesting questions. If anything like this is right on the right track, then it's not answering at this point the most interesting questions, but just raising them and perhaps highlighting ways you might get at them. So in all the work I've been doing for a couple of decades now in probabilistic inference and mental models, you start by showing how you can do inference with a mental model, but then you have to ask, where do you get it from? Now, learning from experience is one thing, and I've done a lot of work, and others in our group and many other colleagues. A lot of that book I mentioned with Tom Griffiths and Nick Chater is about how we can learn using hierarchical Bayes and probabilistic programs, learn abstract programs by doing inference over the space of programs to make sense of our data, maybe even small amounts of data. But much of our learning, probably the most powerful form of human learning, comes through language, more abstract, generic language, as many folks in cognitive science, cognitive development have shown. So the power of language, not only to update your beliefs, but actually to give you new world models, is really incredible. And that's probably that's the real human singularity there, right? Is the ability of language to let us learn and think about situations that we haven't directly experienced. I mean, think about the tug of war, for example. I mean, I don't know if you're like me, I've maybe done one or two tug of war games in my life. Most of my knowledge about tug of war, or my beliefs at least, don't come from my direct experience. They come from things maybe people told me about analogous situations. And more generally, many of our mental models and our intuitive theories come from what people tell us, right? So the same approach that we talked about for updating beliefs from language can also be used to acquire new mental models. But here, what's going on is we're modeling how somebody might explain to you the way this tug of war works. And in fact, in our experiments with humans, and in the Toby Gerstenberg and Noah Goodman and colleagues did, this is exactly what we would do. We would tell people about how this works. People have various strengths. It can vary from person to person. And then now we're using the LLM to translate those sentences in English that are generic sentences about the domain, describing the world model we want our participants to use, into the same kind of probabilistic program code. But now these are defined statements. So these don't condition on a specific world, but they define the general distribution on worlds. But again, they're contextual, they're distributional. There could be different ways of understanding the vagueness in language. But the basic idea is that we can describe a world model in English, and then the code LLM can construct that world model. So all the defined statements now are constructed. They're not exactly the ones that we used in the original paper, but they have the same functional role and they can support the same kinds of inferences. So it's just showing you the way we can, I think, go towards what are the most interesting ways that language informs our thinking, not just as a way to convey specific beliefs about situations, but new world models. And in some most recent work that's still in progress with Tyler Brooke Wilson, Katie Collins, and a number of the others I mentioned here. Tyler is a brilliant philosopher who recently graduated from MIT, and he's actually just accepted a faculty job at Yale. So he'll be at Yale in a year or so. But together with Tyler and others, and Tyler's thesis goes into some early stages of this, we've been exploring the ways that the same approach can support constructing new models, even if I don't explicitly tell you in language how the world works, but just by, again, using your associative memory and marshaling implicit knowledge to construct a model of a new situation. So I could tell you about a relay race, and the relay race is like a new domain. I'm not really telling you how races work. I'm just giving you some information. But we're exploring ways in which the LLM can be queried to construct possible background knowledge and write probabilistic program code that can be suitable for reasoning about this domain. Just on its own, the LLM isn't enough, but you have to do some reasoning about the models that it suggests. And then those models, when suitably reasoned upon, can support novel reasoning in this domain and even sensible updating. So we're really getting, at least demos of steps towards computational models that can capture the richness of how we are able to think about new situations, even ones that we haven't really thought about very much before, or that we haven't been explicitly told how to think about. But using the combination of language, the associative knowledge that's in it, and an underlying ability for constructing probabilistic models of the world and updating. The last thing I just want to leave you with is a set of thoughts about ridiculously
really does have to be the last thing.
It is the last thing. But I think this will set up some of the discussion with Virginia and others too, which is many people in cognitive science, whether in linguistics or other areas engaged in meaning, have been interested in what you could call, a unified account of meaning. And what we're trying to at least point towards steps towards this with the framework I talked about. Just to again raise controversial points for discussion, if you like. But the idea that we can capture the meaning of a word in context, as well as more generally, as effectively, you might think of it as a form of dynamic semantics if you're familiar with this, but the meaning being in context, in a discourse, the incremental contribution to the probability distribution over PLOT expressions in the problem that we're thinking about, or the problem in discussion. And the meaning of a word or phrase or sentence or other unit of language in general is a higher order stochastic function that can take as input a discourse context and return as output a meaning in context. And the idea is that if we think about the different approaches, these are just four traditional ways of thinking about meaning in language, which all have great value and have often been seen as being competitors, ways in which we can really bring them together, ways in which the PLOT ideas that we've talked about can integrate the compositional logical aspects of meaning that formal semantics and other areas in the language of thought tradition have emphasized, as well as in the context of probabilistic language of thought and mental models of the world can give a powerful form of grounding that's not grounded in sense data, but in our models of the world. That's what the PLOT does. And the LLM, or more generally a statistical distributional sequence models, can capture both the distributional statistical aspects of meaning. It's both the sort of distributional usage approach, but also more general semantic association needed to make sense of language so flexibly, as well as some of the very flexible, pragmatic, communicative ways we use language. So I'll just leave it at that. Okay.
Okay. Could you turn off your share, please?
Yes.
First of all, thank you very much for this. There's not a chance in the world that I'm going to forget Virginia this time, and I'll tell you why. Because I'm gobsmacked at how many different areas you're an expert in. And so anyway, here's another one. Virginia Valiant from CUNY Hunter. It's all yours.
Thanks. Josh, that was such a great talk and so rich. In 10 minutes, which is how much time you and I have, will only scratch the surface. So departing from the comments I sent you, with respect to the unified theory of meaning. Many years ago, Jerry Katz suggested that the question, what is meaning, could be separated into questions like, what is sameness of meaning? What is contradiction? What is anomaly? What is entailment? And so on. And it occurs to me that it would be interesting to try this, to try your model, to see just how well it can detect synonymy, contradiction, anomaly, and so on.
Yeah, I think that's a great connection. I mean, I know a little bit about that, but you're inspiring me to go back and reread and learn much more about it. I mean, I think just in the context of the last thing I said, the idea exactly that, in a sense, in this framework at least, what the statistical language model is doing is capturing the notion of sameness effectively, because the distribution on code in the probabilistic language of thought, if that distribution is similar, and that can be measured in different ways, then you might say, well, things have the same meaning, either in context or in general, and that distribution function can be contextualized or it can be made higher order. Okay, so that's really interesting, but it doesn't compute entailment or other, conceptual or inferential relations. Those come from reasoning in the probabilistic language of thought. And yeah, I mean, I think that would be great to explore that more, see if that can account for both account for the different set of phenomena and unify in that sense.
Yeah, I think that would be really interesting to explore. So going back to some of the more mundane, which I guess is a pun, aspects, the way that I'm understanding what you've said about how the theories intersect, that is, how LLMs intersect with Bayesian models, is basically you're using the LLM as a kind of tool to translate from one vocabulary to another vocabulary. Is that accurate?
Yeah, I mean, and that is at the most practical level, that's what we're doing. Yeah.
Okay.
I can say more about that, but let's go with that for now. Yes.
Okay. So the critical difference that I see in what you're doing and what LLMs are doing is well, I guess there are two critical differences, but for me, the most important one is the use of symbols. The other part is the Bayesian mechanism, but let's separate them. So when you put symbols in, to me, you're putting a lot of content into the mechanism. Do you agree with that?
I agree that adding symbols adds a lot of content, but I think, and I didn't have time to unpack all of this very well, I think, but when you say you putting in symbols, in different things that I'm talking about here, the you and the putting in are different. But yeah,
Okay.
whenever you add in symbols, that adds a lot of content and structure. Content.
Right. So I'm thinking about the implications of that for nativism. So it seems to me this is a nativist theory.
I would say it is compatible with some forms of nativism that I find plausible, although I don't have a horse in that game, but through a lot of interactions with friends and colleagues like Liz Spelke, Susan Carey, many others, come to find certain aspects of nativism and conceptual nativism plausible, especially in certain core domains that are shared with other animals, like intuitive physics about objects, that the world is three-dimensional, objects have that there's some kind of physical interactions that our bodies engage with, and also some forms of intuitive psychology, not necessarily higher order belief reasoning, but the idea of efficient action and that agents have goals and they pursue actions in the physical world grounded in physics to achieve their goals efficiently. Honestly, there's evidence, again, Sherry Liu, who did this work in Spelke's lab and continued to build on it, has really, I mean, I was going to say striking evidence in 3-month-olds, but every experiment with 3-month-olds is very small and a lot needs to be built on. But as striking as it gets in 3-month-olds, science, showing that certain aspects of not only physics, but efficient goal-directed action understanding seem to be present. That doesn't mean they're innate, but at least they're present way before language and probably build on some innate stuff. So it's compatible with that notion. Sorry. I'm not sure who that is, but could you mute
That
for
was that was an accident. I think they just should have turned off their.
Okay. But yeah, there's this idea that certain kinds of symbols are used in our framework to describe some of those core systems. But we are, in contrast to like a Fodorian nativism, which says all concepts are innate, in this framework here, I mean, or you could say in contrast, although some of I don't know what Jerry would have actually said about this, but people like Paul Petrovsky have suggested, maybe he would love it. I don't know, but in a rather different version of like some forms of radical conceptual nativism, most of the concepts in this framework are not innate. They're written in a language of thought that could be somehow innate or somehow bootstrapped through natural language. I find some of the ideas that Susan Carey and Liz Spelke in their different ways, along with Jesse Snedeker, have developed their ways in which language acquisition and mental languages of thought might bootstrap each other, and many things in the kind of Lightman tradition also, I think, reflect that idea. But I think we still need to show this. This is like the most interesting thing to do, but to show ways in which the things I was showing at the very end could be used to explain how and model how natural language can start off being grounded semantically and logically in a limited symbolic vocabulary of probable worlds that reflect core knowledge, but then that can support bootstrapping and introducing new concepts via those mechanisms I was talking about at the end, including new concepts, but also new domain theories that we get explicitly or implicitly through our linguistic interaction with other people who we think know more than us.
Okay, that sounds great. It also suggests to me that it is a highly modular system, even though it's also probabilistic. So it's probabilistic within each of these different modules. And depending on what you think the symbols are that you start with, you can iterate what you think the modules of the mind are.
Yeah, no, I think that's right. And I think, I think this framework is not on its own, a proposal for how our minds start, but it can be used to instantiate and build and test some of them. And so I think that's right. It does suggest that you could have, different sub-languages of thought for different domains. But crucially, the picture that you get with adults from this is both in some ways like strikingly supermodular and in some other ways completely holistic. So the striking supermodularity is that the actual reasoning that you do in a discourse, when I'm thinking about a situation and we're talking in a conversation, is very modular. It might even be just specific to this context, what Tyler Brooke Wilson calls bespoke model construction. This idea that we might construct a model on the fly to think about a particular situation. That's that last thing that we've been working on there is in some sense super modular, because that model is relatively small and all the inference I'm doing is just here. So I sidestep or avoid the classic problems of what has made Bayesian inference intractable. The idea that if I'm going to actually have a distribution over all possible worlds I could think about and update that, that's completely intractable. Many people in the nativist tradition, Dan Osherson and others, have written about that. And this is a way around that, or as Tyler puts it in his thesis, it's in a sense a kind of way to think about a solution, certain kind of solution to the frame problem. So it's super modular, but it's also very holistic in the sense that the world knowledge that's used to construct that comes from like all the code you've ever written and all the semantic associations, and it's like a gigantic, holistic, almost Quinean web of language and code, what we've sometimes called the GitHub in the mind view. There's the game engine in the head, the GitHub in the mind. Like GitHub is this, thing on the web, which was crucial for training language code models. And you can imagine your own mind has lots of chunks of code, some of which are maybe innate, many of which are not, and natural language interweaved with it. And having a content addressable associative memory that can use that and marshal out from that relevant symbolic probabilistic models that can be used to reason about a particular situation. In some sense, that's extremely holistic and maybe is necessary to grapple with what is, very clearly some of the holism of human cognition.
So going back a few steps, the intuitive physics part, in principle, animals could do that as well, right?
Yes.
So a chimp could have intuitive physics.
Yeah, and Joseph Call and others have studied that. A number of other, Amanda Seed, a number of others had studied other non-human primates, and we're actually collaborating with Erica Cartmill and some others studying non-human primates on intuitive physics. And I know colleagues who are studying analogous kinds of intuitive physics in rats, and I think even simpler organisms.
Okay, so the difference between humans and other animals is going to be that language allows you to go further. Language allows you to go beyond intuitive physics, whereas nothing is going to help these other animals go beyond intuitive physics.
Yeah, I think that's right. I mean, again, I wouldn't say that all the mental models of other animals is just intuitive physics. They also have models of their social world, like the Cheney and Seyfarth's baboon metaphysics is mostly a social theory. But yeah, but I would say definitely that the key thing here, and it's the real human singularity, I would say, is that language allows us to construct, to both enrich our intuitive physics, to think about aspects of the physical world that are not initially intuitive to us and maybe still aren't, but also to construct things that just go totally beyond any core domain that evolution gave us.
Right. Okay, so one question that this brought up to me, because what you're talking about are all the ways that humans are so good at what they do. But then there are ways that they're not so good at what they do, and far transfer is one of those examples. And there are some things that are hard for people to learn, or some places where it's hard to get from A to Z, even though you think you've learned A. So there's a famous little story about someone going to their logic teacher and asking about understanding if A, then B, and the logic teacher spends a lot of time on that. And the student says, okay, I think I get it. Could we try it with R and S now? So that's something that just shouldn't occur, but it does occur, even with smart people. So, like when you try to teach people about experimental design, it's hard for them to see confounds often. It's hard for them to get at what's wrong with some experimental design. And it's not that they don't have a general intelligence, it's not that they don't have some principles, but it's as if what they've learned is just too far away as far as the string of examples goes for them to get to the next one. So I'm wondering how on your system those kinds of limitations would be modeled.
Yeah, no, that's a great point, a great question, and a great pointer, I think, to work that we could and should do more of. So the stuff I talked about at the very end, which is again the work with Tyler and Katie Collins and Lance Ying and very much with Leo Wang also, is what we're getting at there, like is again how we can describe a situation in language, maybe even very implicitly, just start talking, and then see if this architecture can be used to construct a mental model needed to reason about that situation. And you could also make it better, more robust, if I explicitly give you instructions, as in the educational context you're talking about. If I try to explain to someone logic or experimental design. Actually, another collaborator on that project, said Zhang, is actually very interested for his thesis in how we learn like logic and learn to reason through language. But so we have, our framework is providing possibly a way to do that. But in order for it to work, at least in the current system, we do the kind of thing that LLM folks are generally doing these days, which is some kind of few-shot prompting. We prompt the system with examples of other mental models and language for describing them in related domains. They could be similar or they could be further. And what we already can see, right, is, I mean, the interesting thing is, can you generalize to new domains? So our system is somewhat able to do that. But, you know, this is a place where near or far transfer would be relevant, at least so far, you know, as you might expect. You have to have some domain that's at least reasonably close. And for example, we could transfer from like a tug of war to a relay race or to some other sports setting, or from a couple of sports settings to yet some new sport. Or you might transfer from a sports setting to like a math competition or to some other kind of thing. So really interesting ideas about abstraction and metaphor, analogy, some of the kinds of things that the transfer literature has studied are going to be relevant here. We're just beginning, but what you're pointing to is actually some set of phenomena and things we should really engage with. And I expect, you know, at least based on our current system, it will definitely struggle sometimes with far transfer. Which might be because at that level, you know, I drew this contrast at the very beginning between the pattern recognition approach, data-driven learning, and the mental models approach. But at that level, we are doing a kind of pattern recognition. It's just not patterns in the world, it's patterns in thoughts and thought structures and ways of expressing them. And, you know, at that point, if that kind of really interesting but much more abstract kind of pattern recognition is what's driving your ability to construct new models of new situations, or at least initially, before you've had formal instruction or when you're just at the beginning of formal instruction, then we should expect that it to have the same kinds of fragility with far transfer that any machine learning approach does.
Okay, sorry to be a killjoy here. We have about 10 minutes left, but we have at least 4 people that want to ask questions. So what
Great.
I want to suggest to Alina and Julia and also Lei-Jin and Stefan Carlson is to raise your hand again, and I'll recognize you in the order that you raise your hand. Okay, Julia, go ahead.
Hello. So I was wondering, was thinking like maybe you can use the LLM translator plus the probabilistic models, that system, to model how the beliefs of a reader would change over the course of being told a story or like reading a book. And then you could look across genres or books or whatever to kind of get a sense of what the kind of model of those stories being told, since the stories are themselves a world model, what that would be. And that you could incorporate, because if you have a guess, because something that you didn't like touch on in, you know, in your hacked talk, which I'm sure you didn't have time, but was that like, if you have a guess about where you are in the trajectory of the story you expect, then you have a guess about what you think is going to happen next.
Okay, wrap it up because we have
so I was just wondering, like, do you
Yeah,
think
that's a great question. Let me just try to answer it really quickly. Yeah, Leo Wong would love that question because in addition to being a great cognitive scientist, they are also a writer. They write stories and even novels. And one of the things that we've been working on is little mini like 3-act structures and things like that that follow either classic narrative structures or other things. And you know, maybe not surprisingly, those are places where we see a big gap between human story understanding and LLMs, even the state-of-the-art ones. But exactly, yeah, we're trying to use these models to capture how that kind of you know, journey of understanding might unfold, and also even how a creator might create it. So another student that we've worked with, Kartik Chandra, has had some work at last year's CogSci conference on storytelling as inverse planning, and the idea that like if somebody's understanding another character's journey by doing some inverse planning, as in those theory of mind models, then a storyteller can try to invert that inverse planner to convey the emotional or mental journey that the character has. And that's a way to use this toolkit for both story creation as well as story understanding. So again, those are mostly promissory notes, but great question, and future research, I think, from Kartik and Leo and others will address it.
Thank you.
Thanks.
Hi, I'm going to ask a question in person, Josh. This is Eva.
Hi. Yeah, go for it. I really liked your talk, by the way. I watched it on video. Yeah.
Cool. Great. Okay. So yeah, so following the work that you were showing, where you were basically based also on what you were saying in the question period, where you were, you know, few shot prompting these language models to produce probabilistic language. world models, I guess I have sort of a more meta question, which is, do you see that as just a way to sort of help step-by-step reasoning in these models, or do you think this is sort of evidence for early sort of possible world modeling being learned in these models?
I'm not sure if I see it as either of those. I mean, so I don't think of it as either doing step-by-step reasoning in language models or evidence that they do possible world modeling. It might be I mean, there is, obviously, as you talked about some and others have, there's certainly a lot of evidence that LLMs, if you try to just use them as end-to-end reasoning systems, they can benefit from step-by-step reasoning, and there might be some emergent world modeling capacities. But again, I look at that and I see a really interesting and mixed pattern of successes and failures. And depending on who's writing the paper and what their agendas are, you can highlight the successes or you can highlight the failures and the gaps. To me, an objective perspective is that it's patchy and fragile, although extremely impressive and really interesting. So the way I think of what we're trying to do is to say, yeah, there's various kinds of interesting, approximate, implicit knowledge that those models have that can be used sometimes to succeed in reasoning, complex sequences of reasoning or world modeling. But I think a more robust way to use it is the way we're using it, both a more human-like and a more robust for AI way to use it, which is to condition and construct these bespoke world models that, where the long chains of sequential reasoning or actual, coherent world modeling are there by construction.
Right.
But there are other limits. Like again, as I was saying, Bayesian inference in really complex models is very difficult, and I don't think people do it. There's a lot of evidence they don't do it, but they seem to do it very generally in just the right small model, at least in cases where they have the relevant world knowledge to construct those models. And when they don't, they don't. Right? So that's all. Our minds have mixed patterns of successes and failures there too. But I think this toolkit is better matched to the mixed patterns of successes and failures, which is what I'm trying to get at, if that makes sense. The one that we see in humans, as opposed to the weird head scratching, like super intelligent cases in some places and then super dumb cases in others that you just see in a pure sequence model.
I'm told Alina can go next. Thanks for your answer.
Yeah, thanks for the question.
Alina, pick it up or you lose your turn.
Yes. Hello. Thank you for insightful talk, Josh. So you said that, and correct me if I'm misheard, that language allows us to construct meaning that is totally out of bounds of evolutionary gain. If this is what you said, I think this is deeply profound. So.
Yeah,
so you mentioned.
I'm sure I'm not the only person who said that. Many people have said
okay.
that, yeah.
It's just a reminder,
I do think it's
guess.
profound truth, yes.
Okay, so the actual question. So you mentioned that the meaning of the world is constructed contextually and incrementally. So could you please elaborate on how this process occurs and how it impacts our understanding of complex concepts? So the transition between the from incremental construction of the meaning to generalizations.
Right. So the way it works in I can tell you how it works in the models that we've built so far. And again, this is not to say that it's exactly like this in the mind, but I think it might be something like this. And a lot more work needs to be done. But the way it works in our models is something kind of like what you're familiar in a chat. Like if you've used ChatGPT or other conversational AI systems, the way it's working is that basically if you're used to using ChatGPT, you type something, it types something back. And in the middle, some wheels turn. And then you type something more and wheels turn in the black box and it types more stuff. Okay. So it's basically like that in that you at each sentence is translated into some expression in the language of thought, roughly at the sentence level. And I think sentences are real units of meaning. Like I am very respectful and admiring of many insights from language, including that words are real and sentences are real. And there's real syntactic structure to be understood there that is only being approximated in some ways by these models. But the key is that, yes, there's a process, the contextual process is like at the discourse level. You go sentence code, sentence code, sentence code, and each sentence to code translation is conditioned on the previous conversational history or the discourse that that you have been interpreting. Okay, that's just a first approximation. Just another thing you might want to do, and surely you'll have to do, is go back and edit previous code. Because if you realize, oh, I misunderstood something, I can't just add new code. I have to go back and edit the code that I wrote before, which is also something that code LLMs can do. I'm not saying they'll do it right, but there's other processes that involve like checking and refining and fixing models that are written in this way. But maybe that gives you some sense of the contextual dynamics of how language is understood in this model.
Last question, Lei Jin.
Hi. Joshua, thank you for the presentation. It's very interesting. I have an engineering background, but I'm not an expert in artificial intelligence. I have a few questions. From your presentation, I understand that actually LLMs, it's kind of a gold mine of human knowledge, and you seem to say that they have a modelized real world facts and the logics quite correctly. If you ask the question directly in human language, currently they don't seem to give the good answer because with some lack of algorithm. But if you first translate the human questions into functional code, like the work you are doing, then they are capable of, and we execute the code, then we are capable of having results that are quite close to human behavior. So is that correct?
Yeah, that's more or less correct, but I don't want to, and that's what we've been doing in these examples and what I've been showing. But I don't want to claim, and I don't think it's true, but certainly I don't have the evidence for it being true or how true it is, that LLMs like always do this, right? There's a lot of ways in which language is only an imperfect reflection of the ways that we think. There's certain things that, again, are partly based on evolutionarily ancient core systems that language is not very good at expressing. And that includes also spatial reasoning. And you can see ways in which even the best language models break down here, and multimodal language vision models have had persistent problems always from the beginning there. So I think, I don't want to suggest, I think, yes, language is a treasure trove of knowledge, explicit and implicit, about the world. But and for us, it's such a valuable resource as human beings, okay? That's why it's no accident that language models, when they're trained to capture patterns on all the language that humanity's basically ever produced and put out there on the web, start to have remarkable properties. At the same time, it's only some parts of our knowledge about the world. There's key parts to actually understanding and being in the world that basically nobody ever talks about. and even if they do talk about it, they talk about it very incompletely and imperfectly. And yet our brains are designed to understand in those terms. So I don't want to convey the idea that somehow it's all there in language and that's all you need, not by any means.
Wonderful. Before we let people applaud, there's several panels coming. Are there any of them that you can join? Not today, unfortunately.
Yeah. I need to check my calendar and coordinate on some family things, and I'll try very hard to join one of them. Okay.
Now we'll applaud you for it.
Okay. Thank you. Thanks, and thanks so much for the discussion, Virginia, and all the questions. They were great questions. So I hope to engage more in one of the panels and in person. If anyone here